everybody. Hope you enjoyed a very pleasant lunch. Welcome back to the afternoon session. My name is Carol Mundell. I'm Head of Astrophysics at the University of Bath, and I'll be chairing the session up until the coffee break. We have two speakers this afternoon. I would encourage you to use, again, the social Q&A session that we're testing out for this meeting. You can look online, and we've actually cleared the questions from the morning, so you have a chance of getting your question to the top of the list if you want to type it in there. And again, we'll take a mix of questions from the floor and questions from the online system. So it's my very great pleasure to introduce our first speaker of the afternoon, Professor Nick Roy. Nick is an associate professor in the Department of Aeronautics and Astronautics at the Massachusetts Institute of Technology, and he's a member of the Computer Science and Artificial Intelligence Laboratory at MIT. He received his PhD in robotics from Carnegie Mellon University in 2003, and his research interests include autonomous robots, unmanned air vehicles, human-computer interaction, decision-making under uncertainty, and machine learning. In addition to his academic career, he spent 2 years from 2012 to 2014 as the founder of Project Wing at Google X. So if you'd like to put your hands together and welcome Nick. Thank you.
Thanks very much. It's a real pleasure and honor to be here. The morning talks were extremely illuminating, and I'm really happy to say that I think that there's a consensus emerging, and I think will continue to emerge throughout the afternoon, about what some of the big challenges are. And if you think about the message of, in particular, Andrew and Sethu and Catherine, we saw that it's really... Turn it on. There we go. We saw that it's really about the people. So if we think about what the next big challenges are, the next major steps that have to be taken in robotics and autonomy, it's about more complicated robots, more complicated autonomy that can really operate in populated environments interacting with people. I like to start with the picture of the Wright Flyer because, first of all, I'm aeronautics and astronautics, so I sort of, it's like saying God Save the Queen before you start. I show a picture of the first airplane. But it also illustrates how far we've come from this very man-controlled vehicle to what we have in terms of autonomous systems now. Self-driving cars on the left and one of the drone delivery vehicles on the right. And driving that progress has actually been some pretty big paradigm shifts. And this really echoes some of the things that Andrew talked about this morning. If we think about AI and autonomy and robotics, as recently as 40 years ago, logic, and this is, I think, a good member of the Royal Society, George Boole, logic completely dominated. That if you wanted to write down a problem that had to be solved by an autonomous system, you absolutely used symbolic logic, and Boolean logic and De Morgan's rule was absolutely what drove our representations and how we thought about decision making. It was an inference process. And at the same time, maybe not quite the same time, but about 20 years later, people noticed that really there was a problem with noise in the data, and uncertainty was really important. And Bayesian methods and probability started to appear in the literature. But a lot of people thought that probability and statistics were complete nonsense. This is just not how people reasoned or should reason. And in the early 90s, Peter Cheeseman at NASA was actually compelled to write a paper entitled In Defense of Probability, arguing that this was the right way to reason about the world, and the logicians actually had it wrong. And this was a big debate, but we know the answer now, which is that probability has completely dominated. Probability is the way that we think about robotics and autonomy right now, and there's really very little place for logic right now if you go to the literature, if you look at the papers that are being written, as Andrew and Sethu said, is that there are some fundamental representational issues that probability aren't necessarily capturing. But probability has given us remarkable systems. Just another example of which is here. This is a robotic airplane from my group, and it's using completely onboard sensors. And I like to show this video to sort of show the power of autonomy and the power of these sensors and representations, because this is not the kind of thing that a human pilot could actually do. It's not a particularly complicated trajectory for a human pilot to fly. It's not particularly aggressive in any way, but if you were steering this thing with remote control, there's no place for you to stand. So you can't see the vehicle throughout the entire trajectory. And so this really makes it very difficult for a human pilot to fly. And this is a really good example of why onboard sensing, onboard autonomy are crucial to giving us more complicated systems, more capable systems. I do want to take a minute to just sort of make sure we all understand how these systems work. We've all had coffee. You do remember how to do multivariable differentiation, right? So we'll go through this line by line. No. Some of the things that have made this happen, so how did we get here? So probability helped us without question, and some other changes have happened as well. Obviously miniaturization, Catherine spoke very nicely about this, has been a huge enabler. Miniaturization of computers, miniaturization of other electronic components. The MEMS sensors, driven to a large degree by cell phone technology, has been enormously helpful in terms of giving us more capable systems, more capable robots. And of course, GPS, the third figure there, is has been an extremely enabling technology. But what it's given us is robots that, by and large, are very good at getting from point to point. So we see self-driving cars from the University of Oxford and other places driving down the street very nicely, very, very safely. And we see drones flying around from time to time, again, very much enabled by GPS. And so that's fine as far as it goes. But the question is, what happens when you need to do something more than GPS alone will give you? And so, how many people recognize this picture? So, a small handful. For those of you who haven't seen it, crashed drones are a dime a dozen. Pictures of crashed drones that are taken by the US Secret Service are a little rarer. And the US Secret Service is going to take pictures of drones that crash on the White House lawn. So yes, this is a drone that crashed on the White House lawn. Yes, it is true that some beer was involved. But everybody parted friends, no tears were shed. But it illustrates that there is a problem with the level of autonomy that we have in these vehicles. And in fact, DJI, the company that sells this vehicle, sells about 100,000 vehicles per month, which is an astonishing number. There certainly aren't 100,000 vehicles per month up in the air in any given country around the surface of the earth. So the question is, where are all those vehicles? And the answer is they tend to fly away. And if you buy a DJI Phantom and it flies away and you lose it and you've lost your $2,000, you can go to Facebook and join a support group for people who have lost their vehicles. So the point is that these seemingly smart vehicles that can do all kinds of things for us, that can go and image our house or take pictures of us as we go windsurfing or snowboarding, don't have enough smarts to deal with relatively trivial perturbations from the nominal. And those tend to happen where people are. The other thing that really worries me about robotics and autonomy is that the biggest driver of costs for pretty much any unmanned system, the number one cost is the cost of the labor, the manpower. And that's because for most unmanned systems, we require a team of engineers or a team of operators behind them. This is true even of the big DoD military assets. They have a team of people on the ground. They're all technically pilots. And so there needs to be an inversion of the ratio between the number of people and the number of vehicles. You need to have one person controlling many vehicles. And this, again, is going to require much more from the onboard autonomy in order to make this happen. One of the biggest limitations that we have so far that's making it really hard to let people control many vehicles, or even just let one person interact seamlessly with one person and have the robot understand what's going on, is something that Sethu actually pointed to very nicely this morning, which is that robots right now tend to think very geometrically. So this is an example of a map that a robot might build and might use. And for those who haven't seen this kind of thing before, you can imagine the white stuff is the free space, the black stuff is the location of where the obstacles and walls might be, and the blue stuff is where the robot doesn't actually know what it is. And it's very precise and accurate. And lots of smart people spend a long time thinking about how to actually build maps like this, because this is what most indoor robots and GPS-enabled robots and the self-driving cars, this kind of representation is what's being used to actually drive the autonomy. So they know where they are, and they can plan actions so they don't hit things. But if you were to ask a human for a kind of map, you'd get a very different kind of map. You get something maybe sketched on the back of a napkin. You'd probably get something that looks more like a graph that just basically says what's out there in terms of functionality. This is a conference room, there's a lobby, there's some stairs. And they're all connected to each other in a way where the relative sizes and the relative distances don't matter. And we know that this is what people use. If you think about how would you get outside this building, you don't need a detailed, perfect geometric map. You just need to know that to go out that door and then down the hall and then look for the stair and follow. And if you get lost, you can probably ask somebody. So this really represents a semantic gap between how robots operate and how people operate. And closing that semantic gap is, I think, one of the most important things, one of the most important issues facing robots and autonomy right now. Why is this bad? So what, so what? So there's a semantic gap. People think one way, robots think another, and it's fine. We get along okay. Well, imagine that you're, say, a large internet company, and you're developing a drone delivery service. For whatever reason, you might be doing that. And so you have a robot that's perfectly capable of reasoning geometrically, so it can get from point A to point B, just as I said. And maybe it even has GPS-denied capability, so that if the GPS wigs out for a little bit, it can use onboard sensors to track its position. But how do you actually tell the robot what to do? You probably write down a recipe like this, which is you take off, fly the destination address, enter hover, lower winch, blah, blah, blah. So this is a relatively simple recipe. Fine. Already we see a little bit of a problem in that destination address. Robots, again, think in geometry. They don't know where 77 Massachusetts Avenue is. That's where MIT is. And so, okay, that's not so hard a problem to solve. You're a large internet company. You happen to be good at building other kinds of maps, and so you have to know how to map from that particular address to a point in space. And so you go and look at the point in space that corresponds to that address. And so you see that address, well, the map says that it's the top of the house. And that's fine, except that's a singularly poor place to actually deliver packages. Okay, that's fine. You're a large internet company, you're extremely good at mapping these things, and you know you have drones, and so maybe you've also labeled the nearest point on the sidewalk and the nearest point on the street that actually correspond to that address. And so the challenge, so now the vehicle says, okay, I'm going to land at the nearest point on the sidewalk. Except there's a tree there. Okay, so the vehicle says, fine, I'll deliver to the street. Except you don't want to deliver packages in the street. Okay, so the vehicle says, all right, I have onboard sensors, maybe I'll just look around a little bit. And then you start to realize that the vehicle actually has to start thinking a lot harder about what it was told to do and fold that in. And so it's a much more complicated problem, and it's a much more complicated representational problem. And so this recipe really starts to break down. So how might we fix this? Well, at this point, I'm just going to give some candidate solutions. But one of the ways in which we're going to bridge this so-called semantic gap is to think about the gap really being one of communication. Is that if you have two entities, a person and a robot, that are trying to make their way through the world respectively, and the robot's desperately trying to do what the human wants, maybe writing down a recipe isn't necessarily the right thing to do in terms of just a hard-coded program. Maybe the human and the robot should at least be able to talk about this. And so a version of one of the big challenges that I think is facing robotics and autonomy right now is bringing human language into the robot's understanding of what's going on around it. So robots have sensors. They are laser range scanners or cameras, and they can actually build nice geometric models. Is there any reason why we couldn't think of speech recognition as just another sensor? It's a discrete sensor in that we have discrete packets of words coming at us. But there's no reason that actually has to trouble us particularly. And so perhaps one thing that we could actually do is we could take features of the geometry language. So what I mean is basically combinations of little pieces of things that we've seen in the world and little pieces of the language and put them together and say, I don't know, I'm a forklift, I've seen a pallet, and I've heard the word pallet. And so I can say, right, those things go together. So language and observations maybe correspond to each other. And so if I'm now thinking about the world as a combination of the geometry and a combination of the language that I've heard, well then, that's a representation like any other. And I can actually combine, now I'm a robot, I'm supposed to do things. I can take the combination of what I know about the world and what I've heard about the language. I can actually use that to generate actions for myself. So I can fold this into a decision-making algorithm. And the way that I might actually do this is now it becomes just a math problem. Is I just need to find some function that's actually going to get me from geometry and language to robot actions. And what's a really good, I don't know what that function is. I would be silly to think that I could actually just think really hard as an engineer and write down that function. But what we have seen is that if you have a function to be learned, then learning it from data is really, really powerful. And so what I might consider doing is actually collecting a whole bunch of examples of data that people might say to robots, and I might collect a whole bunch of examples of things that robots see and know, and I might actually learn a function that says how likely those things go together. So that seems a little crazy, but it actually is feasible because language has a really nice property. Language has syntax, and syntax is basically a way of breaking language up. So syntax tells me which bits are nouns and which bits are verbs. Syntax tells me which bits are clauses and which bits are dependent clauses and subordinate clauses, and I can break that up. And so now I don't actually have to learn how to interpret the entire sentence of go find my friend Paul who's wandering around outside and bring him into the hall because he's late. I can actually break each pieces of those. Hey Paul. You can break each pieces of that sentence up into little pieces, and I can say go, and I can interpret that as an action, and I can interpret find as an action, etc. So here's just actually a slightly more concrete example of go past the elevators, through the door, down the hallway, conference room is your left. Each one of those pieces can be interpreted as just a little action, and I actually now have a hope of actually learning what that means. Here's a really, really simple example. Just take the first example, go past the elevators. So again, syntax tells me which bit is a verb, which bit is a location. I have other bits in the language that tell me the shape of the path. And so I can actually look at what the robot knows about the environment and decide how likely any particular action is the robot might take given this language. So let's take the first, let's say, so the robot is, say, a helicopter trying to follow instructions, and it's at a four-way junction. Now let's just make it easy and assume there's 4 different things the robot might do. And here, the robot chooses a path that goes past the fridge. Right, so the robot's clearly going somewhere, so that's good. It's going past something, that's good. But it's going past elevators when you were said, or fridge when you were told the elevators. So it's probably not so good. So if I add up all of those things together, I say, it's probably not the right path. Oops, wrong way. Here's another example. The robot's clearly going somewhere, good. The robot's not going past anything, not so good. And the thing it's not going past isn't an elevator anyhow, so really not good. So this is probably not the right path. And then you get the idea, we're going somewhere past the elevators, et cetera. And so we can actually score these. And so we can take the combination of the words and the stuff in the environment and actually compute the likelihood of stuff in the environment and what the robot's doing and compute the likelihood. Just one tiny little bit more math. How do we actually do these things? So there's some nice, here we get, once again, our friend Reverend Bayes, and he tells us how to actually learn these things from data. Where do we actually get the data? We just, like I said, collect large corpora of data for different example trajectories. So the Amazon Mechanical Turk has had a tremendous impact on human-robot interaction in the last few years, in that you can now take things that you might want to learn and give them to people and say, tell me what's supposed to happen here, write it down. And Mechanical Turkers are willing to label an enormous amount of data for you for relatively small amounts of money. So that's an incredible sea change in robotics, and in particular human-robot interaction in the last few years. And so, can we actually get this to work in real life? We can do, relatively complicated things. So robotic forklift, interacting with a human partner. Human and the robot together are supposed to manage like an outdoor warehouse and stack pallets. When trucks come in, the truck gets unloaded and the pallets have to go somewhere. And the human can now tell the robot various things, the robot will go do it. And it works relatively well. And what's really nice is that by collecting data from untrained people, we actually get examples of the kind of language that people are likely to use. And so we get all kinds of words and all kinds of vocabulary and all kinds of syntax. But what that means is that we actually don't have to require future users to use particular vocabulary. We don't have people heads down trying to control their robots from a display. We don't have to teach them to use a particular syntax or particular vocabulary. It's in the data, which is great. Just one other thing we can do is we can even push this all the way to abstract concepts. So we've actually shown relatively recently that we can actually, given the data, teach the robot to count. We can show examples of what it means for a brick to be the first brick or the second brick or the third brick. And things that you can't perceive, oneness or two-ness or first or second. But what you can do is you can actually learn these from data. And so here's an example of this is a Baxter robot, and it's been taught from previous examples to pick up things like pick up the first in the row or arrange these blocks in a circle. And these are not direct percepts. So now we're starting to get a little bit more towards the promise of logic and back towards what George Boole and others introduced. And then just one last sort of stupid robot trick. We can even do this on air vehicles. So you can imagine an air vehicle teamed with an inspector of some kind. And the inspector is using this air vehicle to actually go and inspect, I don't know, a wind turbine. You know, they're very hard for people to do because they're up high. It's very nice to be able to send an air vehicle with a camera up. But you don't want to have to train your inspector to become a fully qualified pilot. What you want to be able to do is have them actually team with the robot in the most natural way. Go fly up there and take a picture. You know, this is an indoor environment, so we have the commands that the robot is given. But go down towards the elevators. The robot has to understand what an elevator is, and understand what go down means, and all of this is learned from the data. The very last thing I want, there's one other version of this that I just want to talk about at the very end, which is that you don't have to do this just with language. You can even try and bridge the semantic gap in a symbolic way that allows the robot to figure out the kinds of plans without having to build a detailed geometric model at all. So we're walking down the hallway, and we know that the sort of funny oblong-shaped things on either side of the wall are doors. And we do this enough times, and we learn that you can go through doors. And that's a very symbolic representation that allows us to very quickly decide what people should do. If I want to leave this room, the first thing I do is going to find the door and walk through it. Robots don't do that. Robots right now really need a detailed model of free space. And if you really want them to understand doors, you better give them a model of the physics of the door and doors can open, et cetera. And that really doesn't generalize from environment to environment. So the robot kind of has to build a new model of every environment it's in. Wouldn't it be great if you learned how doors work on the left-hand side, and then you transferred that to a new environment that also has doors? It's not the same shape. You know, it's not all indoor environments are exactly the same, but there's enough similarity that you can make useful predictions in a symbolic way about what are useful trajectories. And I'm going to skip this slide and just show, before I just start the video, what I want to do is, pause it for a second. What this is an RC car. We don't have this working on the airplane yet, but the RC car has practiced driving in simulated indoor environments for thousands of hours, where hours in the robot head, it's a few minutes in real clock time. And it's learned the structure and dynamics of environments. And now we've asked it to drive as quickly as possible in this environment it's never seen before. In fact, it's never seen a real world environment of any kind. It's only seen simulation. And it's learned good behaviors and bad behaviors to follow as it drives through the environment. Reinforcement learning is a large field of study in robotics, and it's been working on these kinds of problems for a while, but the challenge is how do you get the representation right? And what we've done is had the robot learn the underlying representation in terms of what it's supposed to do, and kinds of trajectories are good and bad. If I can get the video to play. Shouldn't have stopped it. Come on. Let that playing. There we go. So what you see is that the robot is using a sensor. It's the black laser rangefinder in the middle, and what it's doing is it's seeing sort of obstacles emerge and disappear, but it's learning what's likely to be. It's learned what's likely to be beyond that. So when it gets into a big open space, it knows it can open up the throttle, and it can drive really fast. It's not doing any kind of optimization. It's just using what it knows about the world to actually make good predictions. And then it goes into this very tight corner. It reminds me of the hairpin turn under the Casino Monte Carlo, where you see the Formula One racers gear right down, and the robots learn to do exactly the same thing. And again, this is a very non-geometric representation. This is very much driven by the instantaneous perception and what the robot knows about the world. So just to conclude, I sort of feel like there's 4 big problems that robotics and autonomy have to address in terms of giving us more capable vehicles. And we've done a very good job to a large extent about some of these. We've done a very good job in terms of letting robots know where they are. GPS is great. And some of the more recent work in GPS navigation and mapping estimation, very good at letting robots get from point A to point B. And they can even do so without hitting things a lot of the time. But what they can't necessarily do is they can't figure out what to do next when they get there. They don't yet have a rich enough representation that allows them reliably and robustly to actually execute higher level missions, to respond to the off-nominal, and in particular, we don't yet have great algorithms that give us a way to interact with people and deal with the unexpected. So, it's been a pleasure. Thank you very much.
Many thanks, Nick. Time for questions. I think we'll start with the floor, if anyone has some pressing questions. I'll go to my card first. Well, we have one that I guess could also be addressed to all of the speakers today, but specifically it came about the crashing of drones, which I'm sure is on everybody's mind. Whose responsibility is it when the drone crashes? Is it the user or the manufacturer? And do you want to say something more fundamental and broad-reaching about when technology leads intelligence?
Well, so I'm an engineer, so it's definitely not the engineer's fault who built it. I think it's a shared responsibility. I don't think there's a one-size-fits-all answer. So if you're a commercial operator and you're providing a service on the back of an autonomous vehicle, be it delivery, be it inspection, be it transport, then I think the responsibility to at least the public is yours. It does raise the question of the operator then has to go back to the manufacturer and say, show to me that this technology is safe in some way. And I think this is actually, that now is an engineering problem in terms of how do we actually make, engineering and science, to be honest, how do we actually demonstrate that these systems are capable of the things we want them to be capable of. I was talking to Peter at lunch, and we observed that autonomy, as distinct from automation, is largely about dealing with the unexpected. Automation is where you well understand the environment. It may be dynamic, but you understand it's predictable. Autonomy is dealing with the unpredictable. But certification, verification, validation are about showing that there can be no surprises and that everything is well understood. And those two things are fundamentally in opposition to each other. And I don't think that we have good techniques for bridging, that's yet another gap, good techniques for bridging that gap. So sort of a long-winded answer. Others may have shorter answers.
And at what point does regulation come in there? I mean, the balance between stifling creativity but actually having a top-down approach that you have to meet the standards required by regulation.
Well, so I think that we're very much in a space right now where regulation has very little to say, because regulation is best when we understand what we're dealing with, and we don't understand what we're dealing with. So I think that so in the US, in drones in particular, we have a real problem in that it's very, very difficult, and in fact until last year it was legally impossible for a commercial entity to do any kind of, or any non-public entity, non-governmental agency, to operate a drone for anything other than pure entertainment. So if you're a company that wants to build a new safety system, wants to build a new propulsion system, wants to build new autonomy, it simply was against the law. Done. Couldn't do it. Rules have changed, but it's still the case that it's very hard to test, and so I think where regulation could be most effective, if it has to be present at all, is encouraging the testing and the development, setting up safe spaces and really making it easy for people to do the development. I worry about how hard it is for the two people in a garage to actually get into this kind of technology, because the regulatory hurdles can be so high. And that's where a huge number of successes have come from historically.
Have a microphone?
So that was excellent talk, Nick. Very interesting. I mean, I love the idea of this sort of natural interaction between the operator and the robot. You know, go down there. However, it seems to me that there's a huge potential for misunderstanding.
That's because you're usually underwater, much harder underwater.
Well,
freely admit it.
Yeah, I've tried it. It's very difficult. But you know what you mean when you say. I don't mean at the sort of speech recognition level. I mean at the more abstract level. You know, yeah. I know what I meant to say, but I didn't quite say it right because of how the robot expects to hear it. So I wonder, where are we with? Are we into the definition of grammars and the syntax and semantics that people have to learn to use in order to instruct the robot properly? I mean, where are we with all that at the moment?
So it's a great question. So the answer is definitely not vocabularies and grammars, et cetera. And that problem I describe is, I view that as like, when I nod my head, you hit it, right? So clearly, there's an ambiguity there. And I think that where natural language has actually done us as roboticists a disservice is to actually focus a lot on the parsing and the grammar, et cetera, and really ignore the problem of symbol grounding. How do you ground the symbols in the real world? And the answer to your question is that once you really bite into the symbol grounding problem and actually address the challenge of mapping logical symbols, be they linguistic or otherwise, to the stuff that's happening in the world, very quickly you realize that things could go wrong if you misunderstood it. And so you can then do ambiguity resolution. I mean, the right way to do this is to recognize there's two possible outcomes of your action. One is probably very good and one is probably very bad. And so you should go and ask the person. And we're starting to know how to do that, but you have to have that foundational model that couples the two first.
Peter?
Nick, With your example about robots learning how to open doors, it goes to another place, it comes to a door that it's never seen, doesn't know how to work that kind of door. Mm-hmm. It's going to fail. Mm-hmm. How does it know it's failed? Do you have heuristics to say that indicate that it's failed, or do you have to learn that it's failed?
So great question, and doors are good. I mean, I assume that you also have encountered a door where you attempted to push and you were supposed to pull, et cetera. This happens a lot, or whatever. And so door designers have a lot to answer for, I guess, in that regard. But so first of all, there are cues. So I think so there's this notion of affordance, which is basically a perceptual feature that predicts some action. The handle that's supposed to do this, or the handle supposed to push that. So I think there's a really great intellectual question to be answered there. But that wasn't your question. I'm just saying that there are cues that you can take advantage of when you encounter a new door, and we do that with moderate success a lot of the time. Then when it doesn't work, what does the robot do? And that's an even better question. I think there's a lot of virgin snow in front of us in there in terms of when the thing fails, what is the right response? I think again, you could actually learn this from demonstration, just as we're learning from languages. Like the robot would do what I would do, which is try a few back-off strategies, and then probably abandon the door and either go ask for help or try and find another route, which is usually what I do. And I say usually. And so you would hope that the robot had learned policies that supported that kind of eventuality.
Thank you.
Any other questions from the floor? So maybe just to finish, another one from online. There are a small number of robotic companies, and the question is, how do we get students into these companies to get real-world experience, whether or not the company can pay them to do so?
Yeah, so I come from, I live in the US, and so I have a particular US-centric view on it, which is that right now the only way to get the students into the companies is to pay them. And in Silicon Valley in particular, there are astonishing salaries. So a moderately capable graduate student can probably make about $6,000 a month for 4 months in the Valley, and that would cover about half their tuition for the year. So there's a lot of money, and that's absolutely what's driving a lot of students into the companies. Small companies can't do that, and so they don't get the students. And you can't turn off the flow of money, and so I don't actually have a good answer. In the U.S., there's going to be zero appetite for government funding to make that happen. Yeah. Perhaps that might be a competitive advantage for the U.K. and other jurisdictions, is to actually get the government funding to support students going into the smaller startups.
Okay, that's fantastic. We can thank Nick again for his great talk.